Okay, so last time we talked about this basis pursuit problem, which is a relaxation of the L0 penalized problem. So you minimize the L0 norm subject to a linear system. So this is for the noiseless case where the observations are like a perfect reconstruction of the columns of X by some sparse vector theta star. So you get to see this. You can solve this problem, but it's computationally infeasible. Instead, people propose to solve this problem, minimize L1 norm. This is called basis pursuit regression. It's a convex problem, but the question is that, is it good enough? Can we actually recover theta star? And last time we saw that there's this nice characterization of the conditions under which this will succeed. So this theorem says that if you can recover, like the property that you can recover any S sparse theta star in the noiseless case when you solve the basis pursuit problem is equivalent to this condition being satisfied. Okay. And this condition is in terms of this cone matrix. So this set, which is defined by the subset S, the potential support of the vector is a cone in RD. And again, to remind you, this notation means that we select a subvector. So delta is a vector in RD. We select the subvector that's indexed by S complement, the complement of the support, and delta S, which is this part, selects the part of the vector that's in the support. So this cone sort of says the bad part, this is the bad part, let's say, of the vector is controlled by the good part in the L1 norm. So if you recall, I'm not going to repeat the proof, but the proof was basically that this set is the union of all the descent directions, or that the union of the tangent cones at theta stars that are supported in S. So this is the set that potentially we can decrease the L1 norm if we move in the set of directions along which we can decrease the L1 norm from as far as theta star, if you move in that direction a little bit. And this condition is saying that basically those directions are not feasible. So the kernel of X is the set of feasible directions. So this condition is saying that there is no feasible direction that's also a descent direction. So we can't be both feasible and descent. So theta star has to be the optimal solution. So that's the basic geometric sort of picture. Any questions about this? So writing the descent cone and the feasibility, I mean, this is the feasibility of this is sort of obvious. The descent cone is something like that. The only tricky part was to say that the union of these cones for all theta stars that are supported in S is actually CS. And there's this little argument here that we did last time. There's geometric sort of proof by picture, and then also this proof, which I'm not going to repeat. We will do a similar argument when we prove something about the lasso. But the basic idea is to basically decompose a vector. So this is what we did here. So you decompose a vector L1 norm into two pieces, one under support, one off the support. And then the result follows. Okay, so questions? So this condition is good, but it's not really, perhaps not as informative. So when is it true, or when does it hold? For what x's does it hold? It's not something which is quite obvious. So people have tried to come up with more manageable or more natural conditions. So the first thing that perhaps we can think of is this condition, which is called pairwise incovariance. So suppose we have a matrix X. This should be n by d. And we're looking at, so d is big. So you're looking at the jth column here. So that's xj. And then we take the inner product basically between two different columns, xj and let's say xi. So these are vectors in the n-dimensional space. So I take the inner product and then I also normalize by n. The dimension of these is n, or each one is n. And so if I divide, this is like a normalized inner product. And what this is measuring is how far this is from these columns are being orthonormal. Okay, so if what it's saying is that if this is small, let's say this delta TW, pairwise incovariance, small, it means that if I is not equal to j, this is going to be 0. So this is going to be close to 0. If I is equal to j, this is going to be close to 1. So thinking of these normalized vectors, let's say. So this is roughly, it's saying it's roughly equal to so say much smaller than 1, or like if small, then it means that this is roughly 0 if I is not equal to j, and 1 if I is equal to j. So in this normalized, for these normalized columns are basically orthonormal. And this is basically the best case in regression. So if you have normalized columns that are orthogonal, then so if they are actually orthogonal, I can multiply by, so if you have y, let's say, x theta star, right? If I multiply by xj, inner product xj, so let's write it like this. Y is x theta star, which is summation theta j star xj. So you can write this as this matrix inner product. You can write it as this expression. Basically, you can write it as a linear combination of the columns weighted by theta j. If they were the columns were orthogonal, then I would, for example, do xk inner product with y. And this would be equal to summation j from 1 to d theta star j xk xj. This would be roughly equal to 0 unless k is equal to j. So this would be roughly theta star k, and then times n basically. Okay, yes. So you could recover theta star k, right? Each coordinate you can recover. But of course, the thing is that these are d-dimensional, so you can't have these are vectors in Rn, and d is much bigger than n, so you can't have more than n that are orthogonal, right? So this condition cannot be. This can be 0, but it can be small, and so it would mean that basically the inner product between any pair is small if they're not the same. So if you write this down, you can write it in terms of the grab matrix, which is x transpose x. You can verify that x transpose x, the coordinates are basically these inner products. And this is the so-called vector at infinity. Okay, so this is taking the maximum of the absolute value of the entries. So this quantity is exactly the same as this. The result that is in HDS book is saying a uniform restricted null space holds for all S. Uniform means for all S, with S less than or equal to little s, that the cardinality less than S, if this guy is less than 1 over 3 times S. Okay, so if we can show that this is small, then that condition, restricted null space property, this condition holds for any set S whose cardinality is most S. So this is good because it's relatively easy to calculate this quantity or bound this quantity. It's just a pairwise comparison. So you compare every pair of columns and you try to control this. I'm not going to prove this. This is like exercise 7.3. Probably you're going to prove it in your own homework. Is this sort of clear? That's one condition. It's not, I don't have intuition why this is like this, but maybe when you try to prove it, you can see why that holds. There's a more relaxed condition which people came up with, which is called restricted isometry property. So instead of looking at the L infinity, what this guy is doing is looking at this XS. So XS, if you recall, I don't know if I mentioned this, but you would look at the submatrix of X on columns S. Okay, so that would be XS. So let's say this submatrix is XS. So if I look at XS transpose XS, this is basically it's very similar to this, but restricted to the columns in S. So this matrix is the gram matrix or normalized gram. Yeah. If you increase S, so if you increase S, the parameter becomes less sparse. So this condition becomes more demanding. So it makes sense. So that means your columns more orthogonal. Yes. Yeah. That makes sense because if you recall, you wanted to the condition that we had very early on. I believe it's here. So this was a condition that we arrived at. So you want the, let's say XS to be full rank. Actually, you need X sort of 2S to be full rank if you want to be really careful. What I would do is like if I have, for example, X theta 1 and X theta 2, both of them are sparse and they satisfy this. They have to be equal, and then the difference would be 0. So this difference, let's say this is supported on S1, this is supported on S2, both have size S. The support of this would have size at most 2S. And so you want the columns of X in any subsets of size 2S to be roughly independent, or like linearly independent, to be able to recover this. And as S grows, this condition becomes more severe because you need more, like a bigger submatrix has to be full rank. And this is like a quantitative version of that. It's similar. So what this is saying is that basically the XS, not only is full rank, it's close to being close to basically the identity, or not identity, the isometry. We'll talk about this. The columns are basically, or this one as well. Here the columns are basically, this is like the, we'll see, RIP with S equal to 2. But the condition makes sense because you need more orthogonality of more columns basically. It's a little bit clear here. So to be honest, this one is more clear, more related to that condition that we had. So what this is saying is that this matrix XS, the columns have to be close to orthonormal for any subset S. and for any subset S whose coordinate at most S. So if you compare this with that condition, this is like, you can compare it here. So suppose the columns are normalized to have, the normalized columns have L2 norm 1, then if you look at a subset S with cardinality 2, that would be, so I would take, for example, 2 columns, xj, or xi over root S and xj, sorry, over root n, xi over root n, and xj over root n. And then I form this, so that's my S. So that's, let's say, subset S, cardinality 2. I would take the, this matrix, form this matrix. If you form this matrix, it would be basically xi over n, xi xj over n, xj xi over n, and xj xj over n. Right. So if this is, this assumption holds, these two would be 1. So this would be 1, and this would be 1. And you can see this matrix being close to the identity, which is what this is saying, means that basically xij, this pair is close to 0. Okay, minus this. So you want this to be close to 0. And if this holds, like, this condition holds for all pairs, for all S of size 2, then you would have something like max over I not equal to j is a small. So this would be basically equal to this, if you think a little bit about it. So the condition of pairwise incoherence is roughly, this is stated badly, to be honest. This is in your book, but the delta S, if you have to define it, like if I define it like this, supremum over all S, such that this is like that. If I define this RIP constant to be this, then this is going to be equal to the pairwise incoherence condition for the matrix X if I take S to be equal to 2 and under this normalization. Okay, so this condition is more natural. So what you're saying is that the corresponding submatrix X sub S is close to not an identity but an isometry. So if you believe this, what you can show, for example, is that in general for any S, this guy is bigger than the pairwise incoherence times S times pairwise incoherence. The result is, I'm going to come back to this. The result is that if the restricted null space property holds if delta 2S is less than 1/3. If you compare it with the pairwise incoherence condition that required, for example, this being less than 1/3S. So the conditions are a little bit different. So this one, there's no S in it, and in fact, you can show that it's more relaxed. So why this is called, I'm going to come back to it. I'm not spending too much time on it because these are not perfect conditions. There's a like, people develop this, and then there's a better condition, which is less restrictive. I'm going to talk about this, but the reason why this is sort of called isometry is because if you look at the sample covariance matrix, let's say, think of the columns of X as, or no, actually the rows of X as being samples. Like these are samples, let's say, from a multivariate distribution. So Xi T is the ith row. And let's say if these are zero mean, let's say these are zero mean random variables, this would be an estimate of the sample, an estimate of the covariance matrix of the distribution X. And then you can write this condition as something like that. So if I have the sigma hat, which is d by d, this is just saying the submatrix on S and S. This is easy to verify. This is exactly this. This is close to the identity in operator norm. And so you're saying that this guy is roughly identity, which means that the map X is XS is roughly isometry. So another way of seeing it is let's say for sigma hat SS, this translates to an expression like this. If you expand the operator norm, what operator norm means, that this being less than delta means that for any vector, if I apply this to that vector, the L2 norm is between 1 minus delta and 1 plus delta times norm U2. And this is like an isometry. Isometry would be that if this is equal to U2 everywhere, that would be the identity map. This is also close. And also, this also implies, if you know what isometry is, if this was exactly identity, then XS would be an isometry, which means preserves the norms and distances. But because this is close to identity, XS is close to being an isometry. As I mentioned, isometry is like being orthonormal, have columns orthonormal. This is a good property. This is what you expect to be able to recover. Sort of clear? If you see, yeah, question?
And so the restricted nulls, that property is just the intersection of C of S and X. That's what
that property is, yes.
Like, what is the property?
Why is this useful? Yeah, so why do we care about this? So the answer is like on this slide. Yeah, so this property is equivalent to being able to recover theta star. So if this holds, then I can recover any S sparse theta star. And if this doesn't hold, then there is a theta star supported here that I can't recover. I get like a different answer. These conditions are natural if you think about, so just naturally, if you think about regression, if I have two columns that are exactly equal, then have you seen it in regression? This has a name. So if columns of the design are the same or correlated, very correlated, what is it called? Collinearity or multicollinearity. So I have multiple columns that one can be written in terms of the linear combination of the others. Or let's say if I have two columns, they're scaled multiple of each other, or they're exactly the same, then theta star is not identifiable. This is true in general, because I can sort of shift the weights from this column to this column. So if this was theta star I, theta star j, I can subtract from theta star I, put it on theta star j, and because of this equation, the result doesn't change. If xj and xi are the same, I can just rearrange the weights on both as I want. And so a sort of independence, linear independence is required. And this is a little bit more. So this is saying it's measuring linear independence if you normalize the columns. So if you normalize the columns, the inner product basically measures how, if you remember Cauchy-Schwarz, if the inner product is 0, they're perfectly orthogonal. If it's close to 1, then they're almost in the same direction. So that makes sense in the sense of uniqueness of theta and being able to recover. But why, for example, this is just something that I can't give an intuition. You know that it should be small, but how small is something that you determine.
So if the multiple linearity is here, probably the solution probably is not so unique.
If there is multicollinearity, yes, there is.
So how to transform this to the restricted non-space problem?
So let's say it's clear, for example, from this, let's say this one. What this is saying is that this is close to identity. This means that the columns of XS cannot be multicollinear. You can verify that if this is, let's say, it's less than 1, then for sure that's not the case. For the signal space property, I'm going to talk about that later. So these conditions, there is a cleaner version of these, which makes a lot of sense. And also it makes a lot of sense from the regression perspective. That's why I'm not going to spend too much time on this. I just want to point out that these are out there. So in case you see this, this is like progressively more relaxed conditions. If you do this, so compare, this is proved in the HDS book, this property. So if you have a RIP condition of this form or pairwise invariance condition of this form, then the restricted normal space property holds, and then so you can recover. This exercise, I think, will be in your homework problem. You can show, so the question is that when do these hold? Again, for a general matrix, it's not easy to necessarily verify. I just want to maybe emphasize that, like in practice, it's hard to verify because you have to search over all sets S of size S to try to verify this. So why do people care about this? Because theoretically, you can show that for certain classes of X, this is true. In particular, if X is random, people can show that this holds with high probability under certain assumptions. This is, for example, the typical case. Suppose I have an X whose entries are sub-Gaussian, IID, and then the expectation is 0. The basically variance is 1. Then you can show that for you to have this, it's enough to the sample size to be n bigger than or equal to a constant times s squared log d. So this notation again, if you recall, n is bigger than some universal constant s squared log d. So if the sample size is this big, then that the pairwise invariance condition holds. This is saying that if the sample size is this big, then the RIP holds. And you can see the difference is this factor of S. So this requires more. This requires less. So this is a less restrictive condition in the IID case. And you can improve this. So later on, maybe at some point, we'll see that you can't have less than this much sample. You can recover. So the RIP in this case gives you the optimal sample complexity. But that's one of the things that people worry about. Yeah.
For this slide, what are we finding with high probability?
Oh, this one?
That's like big down there.
What do we mean by with high probability? So one thing, for example, is something like, it's a good question. Sometimes we mean this guy is less than this. The probability that this is bigger than 1 minus something which is O of 1, as let's say n, s, and d go to infinity. Okay. Usually there is some sort of a probability here explicit, like c over, for example, d. This means that if d goes to infinity, this is going to 0. Yeah, I'm being a little bit vague, but generally speaking, there is some term here that gets small. Let's say if all these parameters go to infinity and they satisfy this relation. Okay, so let's say something like this. We'll see like more explicit examples. C1 and ds, and then this goes to infinity, sort of. Goes to infinity as, let's say, nds. This is also not that accurate. So this, what does it mean for this go to infinity? You could put it to infinity different ways. Basically, if they get large, this gets small. That's rough idea. But you're going to prove an explicit result in 7.7. You can check Usually in these cases, D has to be large for this to go to 0. But the main point is you can see the restrictiveness. One thing that is bothersome in this type of result, in this exercise 7.7, is that these are IID. So Iid Design, so this is saying all the entries of the design matrix are independent. So basically, if you recall, every row, the rows are independent in regression. That's a reasonable assumption. But you generally, these entries in each row are the covariates. And it's a very restrictive assumption to assume that the covariates are uncorrelated. So usually covariates are correlated. So generally you would like to have each row come from a normal, let's say with mean 0 and a general covariance matrix. And so this result falls apart. That's exactly sort of the reason why people try to move away from this. Suppose you have a more general covariance matrix, and let's say xi is the ith row of the design. This is the ith row. Ith row. This is xi. So this is normal with mean 0 and sigma. And suppose, for example, that sigma looks like this, like a convex combination of the identity and 1 transpose. 1 is the vector of all ones, and 1 transpose is transpose. So this matrix 1 transpose is just the vector of all ones. So all ones, d by d. Okay, so if you think about this, on the diagonal, basically, sigma would look like 1, 1, 1. And off diagonal, it would be just mu. So it's a covariance matrix whose entries on the diagonal are 1, everywhere else is mu, and mu in 0 is in 0, 1. Sometimes this is called the spite covariance matrix because of the eigenstructure. Anyone knows the eigenvalues and eigenfunctions of? What are the eigenvalues, eigenfunctions, like the eigenvectors of this? So what happens if I have a matrix? What happens to the eigenvalues if I add a multiple identity to the matrix? We just shift the eigenvalues by 1 minus mu, and it doesn't change the eigenvectors. So it's enough to figure out what the eigenvectors of this matrix are and eigenvalues, and then I can shift the eigenvalues, retain the eigenvectors. What are the eigenvalues and eigenvectors of that matrix? So what is the rank of that matrix? 1. So what is the conclusion about the eigenvalues? It's a square matrix. Sorry? Mu or 1 minus mu? This one? So one of the eigenvalues is, so how many 0 eigenvalues do we have? How many non-zero eigenvalues? D minus 1 zeros and 1 non-zero, okay? And then it's easy to guess. So let's say I would guess that the non-zero one is multiplied by 1, right? This would give me mu 1 times d, right? Because 1 transpose d. So you can see that 1 is an eigenvalue corresponding to eigenvector mu d, right? So this would be mu d1. So 1 is the non-zero eigenvector, and this is the eigenvalue, right? Or you can normalize it 1 over root d if you want. But there is one non-trivial eigenvector, which is in the direction of 1. That's the spike. The rest of the eigenvectors are eigenvectors of like the identity matrix orthogonal to 1. So any like the subspace orthogonal to 1, if you pick any basis for it, that would be the rest of the eigenvectors. Yeah, and then the one eigenvalue is mu d, the other ones are 0. So the eigenvalues of this are eigenvalues are 1 minus mu plus mu d and 0. This is 1 times. This is d minus 1 times. Okay, so these are the eigenvalues. And then by the same argument, if you look at sigma SS, which is the submatrix on subset S and S, this submatrix is, again is a matrix of this form because of the symmetry, right? So if I take the subset S here, and the subset S here, if you look at sigma SS, it still looks like 1, 1, 1, and then mu everywhere. It's just now the size is S by S, little S by S. And so the eigenvalues are exactly the same, but you get 1 minus mu plus mu S, that's the largest eigenvalue. And then the rest are, so the largest eigenvalue is this one. So 1 minus mu plus mu d is the largest one, or 1 plus mu times d minus 1. And the same holds for this, with d replaced with s. So gamma max, this is your notation, like HDS notation for the maximum eigenvalue. So the maximum eigenvalue of this is that, and you can see that as s goes to infinity, this is going to infinity. This suggests that the RIP cannot hold. So RIP assumes that, so RIP says for any subset S, this minus the identity matrix, the operator norm should be less than something less than 1. Okay, if this is true, then all the eigenvalues of this are going to be within delta of the eigenvalues of this. Eigenvalues of 1 are 1. If you recall the Valence theorem that I mentioned last time. So gamma, let's say these are the eigenvalues, minus gamma I of I. This is bounded by the operator norm. This is the Valence theorem. And this would be less than or equal to delta. And so these are all 1. So this is saying gamma I of sigma SS has to be in 1 minus delta and 1 plus delta. So if RIP holds, all the eigenvalues are within like a little band around 1. But this guy, you can see for any mu non-zero, if mu is 0, we're back to the IID case. But if mu is tiny bit bigger than 0, then as S grows, either S doesn't have, even if S doesn't grow, you can see, because I want this to be less than, so the, if you subtract this from 1, right? So RIP is basically saying, so gamma max. So operator norm would be absolute value of gamma max here. So that's the operator norm. This is the, let me do this. So it's not hard to see for symmetric matrices, the operator norm is the absolute value of the maximum eigenvalue. And this is just the absolute value of gamma max sigma SS minus 1. Now, as I mentioned, if you subtract identity, just shift eigenvalues. So this being less than, so this being 1 plus mu s minus 1 means this is bounded basic. This is like mu s minus 1 further bounded by mu s. So I want this to be less than delta or less than 1. So this is saying that mu has to be less than 1 over s, roughly. Okay, or has to be like less than 1/3 actually. Right, so it has to be like this. So mu has to be less than 1 over 3s. And okay, there's something wrong here. So what I have here is a little bit better. So PW is violated unless mu is much less than 1 over s. RIP is violated if mu is 1 less than root s. Is this correct? So delta 2s grows like mu root s. Is this true? Did I make a mistake here? Exercise 7.8. So what the other calculation shows is that the RIP sort of scales like mu s, not mu root s. RIP constant. Can anyone find out how I made a mistake here? Did I make a mistake? This is a little bit better. So this is, generally you'd expect RIP to be more relaxed. So root s smaller than, is it smaller or bigger? Yes, it's smaller than s. So this is bigger, so it's more, yeah. But where did I make a mistake? Why didn't I notice this before? So RIP is this. And so what I'm doing is that I'm applying the RIP to the population version, not the sigma hat, but I'm applying it to. So sigma hat would be close when x is random. Sigma hat is close to hopefully sigma. At least you need RIP on the population sigma. And what I'm trying to do here is apply the. So we're analyzing the population sigma, not the random sigma hat. That should give us even a better condition. But something is not right here. Anyone can see? Did we do anything wrong here? Camel max. I did some little calculation here. So if you look at RIP assumes something like this. And the condition was that this is the RIP constant. So you want this to be less than 1/3, let's say, for all s's of size s. And this quantity is this. So it's a symmetric matrix. The operator norm is absolute value of the maximum eigenvalue. And then this is equal to this. We did the calculation that the maximum eigenvalue, this is 1 plus mu s minus 1. And this is suggesting that if this is like bounding this by s is minimal. And then, so the condition, the RIP condition for this matrix on the population level will be mu s less than 1/3 or mu less than 1/3s. But what I have here is this delta is growing like mu root s, not mu s, which is better. Okay, so let's reconcile this later. There's this caveat here. But generally speaking, either this or that, it's very restricted. So as s grows, let's say d grows, I can let, yeah.
I have a question about the setup for RIP.
Yeah.
How do we know that the delta is less?
We don't, that's part of the condition.
That's just the assumption is that delta is less than, or that's what we need.
So you, let's say the RIP is defined as the maximum, like the RIP constant, let's call it, is the supremo order. So what we need is, if this is less than 1, this is a sort of an RIP condition, because then this makes sense. So this is saying this is bigger than 0. This is bigger than 0, so the norm of this is within like a constant factor of u2. If this is negative, then this part is useless. And then, in fact, for the result that we need it to be less than 1/3 even. So this is part of the condition. Yeah, just let me see if is it done?
Yeah, I just don't see the equivalence between that line, the delta less than 1, and then the actual definition.
You mean this one?
So that line versus the definition down at the top, I'm missing.
No, what I'm saying is that, okay, yeah, so let's say if so let's say if RIP holds, RIP, the way that's defined, if RIP holds with delta S x less than 1, then the rest.
Yeah, sure, that makes sense.
That's what I'm trying to say. Yeah, so an RIP condition where this is bigger than 1 is like useless,
Okay.
right? It's yeah, the wording is not ideal. So what I'm trying to say is that let's say RIP holds with delta which is less than 1, then this holds and this is,
Sure.
yeah. Yeah, these slides are a little bit bumpy. Is that done, Victor?
Yeah, I just thought the definition implied
No, this is just no, there's no need.
Okay.
This could be big. As you can see, like here, this could grow. This could easily be very large. There's no assumption. Okay, yeah.
I have a question about the probabilization. So, do I understand it correctly that the problem is that mu is not supposed to be larger than 1 over s? Because both of them, so far, we know that if mu is, we already proved that mu is smaller than 1 over 3s, right? So it's obviously smaller than 1 over 3 square root of s. But the problem is we want to show that it also has to be smaller than.
No, I'm not. I haven't proved. So this is like I want this to hold. I want this. So maybe I did it the other. So we want this to be less than 1/3 for all s, such that this is equal to little s. And then calculated, this is equivalent to saying, if I did it right, mu s minus 1 is less than 1/3 for all s less than s for s, right? So that's the condition that I need. But the claim there is that
It's not as tight
as yeah, so a more relaxed version would satisfy this rather than this. That's what is a little bit problematic. So let me. I forgot. We are like either we're making a mistake here or this is not correct. But I'll get back to you. You can think about it as well. But in any case, either one, so you can also verify this for yourself that pairwise invariance would be violated with high probability unless this happens, and this is the case for the RIP. And these conditions are generally implying if S is growing at all, this means that the mu has to go to 0. So you can't have these conditions for a design for which this mu is constant. Later on, but by a result that we show that in fact for any mu in mu and 0, 1, basis pursuit succeeds with high probability if this condition holds the same sample complexity as we had for the IID case using the RIP. Under the same thing, it would work out for all these matrices except mu being equal to 1, in which case things would break down. And this is based on using the actual restricted knowledge space itself, or like a relaxed version of it. So this slide just tries to summarize why people moved away from RIP and pairwise invariance because of the situation with correlated design and the severe constraint that these conditions put on the non-zero entries, like the off-diagonal entries, if they're going to be satisfied. Okay, we'll try to fix that issue later. Questions? So what I want to do is like we'll see the better condition. It's actually not the better condition. Sorry. We're going to stick with this basically. We're going to stick with this, but we're going to relax it for the noisy setting. It becomes a little bit maybe more natural when we relax it, But the thing is that this condition itself is relaxed enough. This is good enough. In the random case, you can work with this and you can get results that are, for example, they cover this correlated design, while these RIP, these things won't work there. So let me just move on to the noisy sparse regression. Things might become a little more clear. So in this case, so basis pursued, recall, was minimize L1 norm subject to y equal x theta. And this is useful if we know that there's no noise. But if you have noise, then this condition, like trying to satisfy the linear system exactly, is not that sensible, because you know there's noise in y. You don't want to be exactly equal to y. So you do usual regression, so L2, least squares regression, and then you add the L1 as a penalty. Or you can add it as a constraint. And by Lagrange duality, they're sort of equivalent. So for every lambda, there is an R such that the solution of the two problems are the same. For the most part, you're going to work with this penalized version. But results for this are easy to obtain as well. Actually, we might actually prove a result for this first. I forgot, and then prove it for this. But let's keep both in mind. So these are convex problems. Global solution can be obtained efficiently. So now what we want to do is we want to assume that y is coming from a noisy model. So there's x theta star plus some noise. For example, wi's are, so w is w1 up to wn. Say wi's are independent, zero mean, say sub-Gaussian with sub-Gaussian standard. Sigma. The question is that can I still recover? So in this case, we need to upgrade the restricted null space property, and the upgrade is this condition, which is referred to as restricted eigenvalue condition. So we have the same cone, but now I'm going to allow for a parameter here, alpha, which may not be 1. So before it was 1, we have to like relax it a little bit, and this cone we relax it. But then this condition is a strengthening of RNS, the restricted null space property. So what this is saying is that for any delta in this cone, this inequality holds. Okay, for some kappa and alpha, and these are the parameters of the RE condition. So if you think about it, the RNS corresponds to this version, where this other side is 0 for any non-zero vectors in delta in a C1s. So maybe one of you wants to tell me why this is equivalent to restricted null space property. So restricted null space property is C, let's say 1s in this notation, intersect kernel of x is the trivial vector. So the claim is that this is equivalent to this. And then if you compare these two, you can see this is strengthening. Instead of 0 here, we have something which is proportional to the norm of delta. So this form clearly shows that this is stronger than this. But why this is the same as this? Yeah.
Because if that one layer square to norm is equal 0, then it means that delta is in null space. Sorry, kernel X, and then it would be like the intersection would not be just 0.
Good, yeah. So suppose there is a non-zero vector for which this is 0. So non-zero and delta is in C1s. So delta is in C1s and it's not 0, but this side is like always bigger than or equal to 0. This condition is basically equivalent to saying that this is non-zero. So what happens if this is 0? If this is 0, it means that x delta has to be 0. Okay? X delta has to be 0, which then means that x delta is in the kernel of x. So the condition is violated if there is a non-zero vector here that's in the intersection of the two. So that's if and only if, which is, so this is violated if this is violated. Okay. So think of the logical knot of this and the logical knot of this are equivalent. Right? If this is violated, then there is a non-zero vector which is in the intersection of the kernel and this. And if this is violated, it means that there is some non-zero vector which is in the intersection of the two. So this is equivalent to RNS, and then this condition is a strict improvement or like strengthening. So now why this is called restricted eigenvalue condition? Anyone can sort of this part has nothing to do with the cone. The alpha here has something to do with the cone. Yeah, so this causes actually, is it narrower or in a sense wider? So if, let's say S complement is, so what was the setup that we had before? So S is 2, right? S is 2, S complement is 1. That's the cone. So if I add like a constant like 3 here, it means that delta 1 is less than 3 times. So what is the line delta 1? 3 times delta 2. Is it narrower or? So maybe copy paste it. Copy. Go there. So how about delta 1, let's say delta 2, delta 1 less than or equal to 3. So if I say like delta 2 is equal to 1, right? In the previous case, this would be 1. Now it's saying that the delta 1 has to be between -3 and 3, right? So it's like fatter, basically. So it goes all the way to, yeah, this is 1, 2, 3. So it looks like this, I believe. So the condition is more strict, you can see. So now that's the, like this is the new cone. So the condition becomes stricter because before the null space has to pass through. Opposite. I was hoping that this is correct. So delta 1. Yeah, you can look at the level sets. If I set it equal to 1, it should be an interval right here. It seems correct. So what this is saying is that before, let's say the null space could pass through, let's say here. If it passed through here, it would miss the cone except at 0, but now it's included here. So the range where this is valid is sort of, if you do it, it's that, yeah, if you do it like with 3 here, this is a stronger condition. We're even relaxing it more. It's not going to be like this. There is a picture in the book, I think. If you look at this thing, it would like change the structure around the 0 as well. So there's some sort of a area here. It can't be like 0 here. I forgot the good way of doing it, but sort of it would look something like this. Because of this lower, non-trivial lower bound that we put it, it's not exactly a cone anymore. But this is a cone, but the condition would be a little bit, I should forget that this is the case. Let me take it back. Yeah, if you do RNS, it's just going to be, the 3 would be stronger condition. We're actually operating it to this, having this non-0 part there as well. So questions? So why this is called restricted eigenvalue in one?
The eigenvalue satisfies that eigenvalue with an absolute value.
Sorry, okay, so I divided it, then what?
So like for any delta, which is eigenvector,
Yeah,
like you're gonna get like a lambda times delta numerator.
yeah.
So you can pull it out and the delta, norms of delta will cancel. And so you're bounding the absolute value of the eigenvalues away from 0.
Okay, great. Yeah, so that's so let's call right. So what I want to do. This is not correct. So let's do this. This is the condition bigger than or equal to kappa. So if you compare, I'm dividing it by the norm of delta squared. So this is saying this is bounded below for any delta in C alpha S. Now I'm gonna rearrange this a little bit. Let's call let's define y to be 1 over root nx. It's like the rescale. That's the scaling of the columns, if you recall, or this is very common. So in terms of that, this would look like this. There's a square here missing as well. Bigger than or equal to kappa. And then I take the square root, let's say it would be, actually, let's not do the square root. So if delta is an eigenvector of y, then we have like y delta is lambda delta. So if I plug that in, I get top would be delta lambda squared divided by delta squared bigger than or equal to k. So things cancel out. So say lambda squared bigger than k, or this is bigger than root k. Okay, for any eigenvalue. So you're lower bounding all the eigenvalues. So assuming this was like true, so let's say this was true for all delta not 0. So if this condition was true for all delta not equal to 0, not just these restricted ones. So this condition for all delta not equal to 0 is equivalent to bounding all the eigenvalues from below by a constant. Yes.
So, wait, can you repeat again, like what was the condition that made the code have those like?
I took that back because I'm not sure if that's. I'll get back to you maybe on this.
So then this condition only tells you about eigenvalues who have eigenvectors.
So that's you're good. So let's say I'm gonna forget about the restriction here. Suppose this condition was true for all delta not zero, right? If that was the case, let's say this condition, suppose this was true for all delta not equal to zero, not this. Okay, if you have that, then that condition would be equivalent to saying that all the eigenvalues are bounded below. In other words, if you you know a little bit of, so this is the variational characterization. So lambda min of y is well, let's say the not the lambda min, but what do I want to say? Yeah, so basically lambda min actually. Lambda min of y is inf y delta divided by delta. The maximum of this is the maximum eigenvalue, the minimum is the minimum eigenvalue. This is like the Rayleigh quotient type idea. And so you can see immediately that this bounding this is bounding the minimum eigenvalue. Or as like Kyle had, this is good enough. This is showing that all eigenvalues. So the minimum has to be bigger than this. This is like bounding the absolute, like the absolute value of the eigenvalues. We don't have to worry too much about this. But the main point is that we have this condition for some delta. That's why they call it the restricted eigenvalue condition. It's not that the eigenvalues are no longer going to be necessarily in the cone. Sorry, the eigenvectors are not going to be in the cone, but this is as if you're bounding some sort of an eigenvalue, right? You're minimizing the minimum of this or all non-zero delta is the minimum eigenvalue squared. So the minimum of this over all of this is some sort of a restricted eigenvalue. It's like a definition of restricted eigenvalues. Okay, so what happens if I do like go in these directions, how small this can get. So you can see that the eigenvalues measure how small this ratio can get without any restriction on delta. This is saying how small can this get if I just move in these restricted directions. Does that make sense? Like, and it's very related to basically the curvature of this quadratic form. So this is measuring is a form of a curvature of that.
So it's more relaxed because you don't need to, you just don't need to hold this happening.
Yes, it's much more relaxed than this. So the main point is that this cannot be satisfied if y is, yes, exactly. So if y is n by v, which is our high dimensional setting, this has a lot of zero eigenvalues. So the minimum eigenvalue is zero. So this is going to be zero for a lot of directions. This is saying let's restrict ourselves to certain directions. There is hope that this is satisfied. So you don't have to. So if you view this function actually as a function of delta without any restriction, it's something like. It's hard to plot, but in high dimension, there's a plot of this in the book. There's a huge, how should I plot it? Not good at this. So imagine like quadratic forms that are sort of shifted. It's like something like this, okay? In this direction, this is the direction of the kernel. In this direction, if you move, the function doesn't change. So if you move, delta moves in the kernel of y or x, the function doesn't change. And so in these directions, there is no curvature. But in these directions, there is a curvature. So if you restrict yourself in this direction, you see a very curved surface. But if you go in this direction, so everything sort of is flat. So what this condition is trying to control is that, let's say for a random x, this direction is not, this is not a random direction. It's a very specific direction. So if you like take a random x for these deltas, basically you see this view, not this view. In any case, it's just geometrically you're right that this is not this is very strong, and in fact it's not possible to satisfy it in high dimension. So that's why the whole point is that this is much more relaxed an eigenvalue condition. It's a restricted eigenvalue, but it's actually more relaxed than an eigenvalue condition. Okay, an eigenvalue condition would be equivalent to saying like X transpose X is invertible, or X is full rank. This is the condition that you need for what? So this is something about this is something about the eigenvalues of X transpose X squared. It's just delta transpose X delta. I should have done this. It would be better to do this. So lambda min Y transpose Y is basically in delta transpose Y delta. This is a little bit better. I'm happier with this. For any matrix, we'd have inf. For any symmetric matrix, delta A delta divided by this. This is going to be the variational characterization of the eigenvalue. So what this is saying is that the eigenvalues of this are controlled. If the minimum eigenvalue is bigger than 0, then it's invertible, and that you have like usual least squares regression. This is a milder assumption. Questions? Okay, so let me just mention the result next time when we prove it. So suppose we have this random, it's actually not random at this point. So we have this noisy version. This is a deterministic result. We're going to find conditions on W for which we can have perfect, or not perfect, but we can have approximate recovery theta star. So we have this noisy version, and then theta star is supported in S, and X satisfies the RE condition with kappa and 3. 3 is the like the relaxation of the cone. It's exactly that 3 there. Okay. C alpha is 3. Let us define Z being X transpose W over N. That's some sort of transform noise. So the result is that any solution of the lasso at the penalized problem with lambda, which is our gauge parameter, if it's bigger than 2 times the infinity norm of Z, then we have this bound on the how close the solution of the lasso is to the truth. And any solution of the constraint lasso with R being the true, that's the radius. If you recall, that's the radius of the radius we use in the constraint. So this constraint lasso with R being this L1 norm of theta star would have a similar condition. You can see the smallest, we want lambda to be the smallest possible because that would decrease the bound. So if I plug in the smallest lambda that's permissible by this, I get 2 times Z infinity. You can see the bounds are almost the same up to constants. Okay, so let me mention very briefly why this is an interesting result. Then next time we're going to prove it. So this is deterministic. So suppose now that X is sub-Gaussian, or actually Gaussian for simplicity. Suppose W is Gaussian with norm 0 and variance sigma squared. We're going to impose this normalization condition. So the columns of X divided by root and the norm is of most C. And then Z, recall that Z is X transpose W over N. You would show in your homework problem, using the techniques that we have seen so far, that the Z infinity is actually with high probability, that's the high probability. Okay, with probability bigger than this, there's a slack delta here, and then the N there, so N goes to infinity, this goes to 0. The Z infinity is bounded by root 2 log V over N. So the log V shouldn't surprise you because of the infinity norm. And if that's the case, I want the lambda to be bigger than 2 times Z infinity. So basically twice this is good enough. So if I take lambda to be twice this, it's going to be bigger than 2 times Z infinity. And then the bound was theta hat minus theta star less than up to a constant root S lambda over kappa. Kappa is the restricted isometry constant. So you get root S times this lambda. So this lambda. So you get root S here, and then lambda, and the rest of the business. And then you can take delta to be of this size. So So the end result is something like this. So you get that this is bounded by sigma root s log d over n. With probability 1 minus 2 times d minus 1. I'm going to come back maybe next time, make it a little more clear. But this is a very interesting result because without knowing the support, you're achieving a bound which is not like root d over n. So if it was just usual regression, you'd expect root d over n, but you get root s log d over n. If you knew the support in advance, what we would get if you like just did the regression on the support would be root s over n. So the only price that you're paying is this extra log d here. And that log d is the price of not knowing the support. You're sort of searching over the d choose s or d to the s candidate support. So you have to pay a price, but the price is logarithmic in d. So this shows like a consistency. So if it's met n as much bigger than s log d, this is basically the sample complexity. If it's much bigger than log d, this is much bigger than 0, like 1. Or you can say that if I want that this be less than epsilon, it's enough to have this being bigger than like a constant times epsilon over 2. Sorry. Yeah, n bigger than or equal to s log e over epsilon squared. So that's the sample complexity you need to achieve a certain restriction. It's proportional to s and also log d. Good? Yeah.
Wait, so just constrained classes not dependent.
There's no lambda yet because there's no penalty. There's just this r. It's like the corresponding parameter here. Lambda is for the penalized one, r is the radius of the constraint. Okay. Okay, thank you guys. See you guys next time. We'll do the proof.